final talk in this session is going to be given by Zach Mulhollan, also working in the lab with Dr. Qiao. And he's going to be talking about the optical differentiation wavefront sensor and his model of wavefront reconstruction and error.
Thank you, Aaron. As he said, I work in the AOFIM lab with Dr. Qiao. Aaron himself also collaborated with my project here. So today I'm going to talk about how I developed a model of an optical differentiation wavefront sensor. There's a physical setup of an optical differentiation wavefront sensor set up in our lab. So I set the parameters of the system to replicate what we have on our optical bench. We're going to use this model to measure error introduced when our transmission filter is misaligned along the z-axis. I'll talk about the transmission filter later on. And there's also accuracy dependence on focal spot size and how it fills our transmission filter. So what is a wavefront? It's defined as a surface in which an optical wave has constant phase. It's orthogonal to the direction of light, as you can see in the animation on the right. It can change shape as it travels through a medium such as atmosphere, a lens, or the human eye. And as deviation of a wavefront from a planar wave is called a wavefront aberration. So as you can see, the thicker part of the lens slows down the light more than on the edges, and that's how you can focus down light. And in optical metrology, it is necessary to have a precise method to measure the shape of the wavefront. That way you can tolerance the system. Say, if a lens has a focal length that it says is 1 meter, you can actually measure the wavefront shape and see if it was accurately measured. So the optical differentiation wavefront sensor, shown down here, it's a 4F system. It has a transmission filter right there. It's basically like a telescopic setup, only there's no magnification. You're only interested in this field right here. So you start out with a light source. We use a Heaney laser in the lab. Here's the input plane, so that's whatever object. Usually we're using a lens that you want to measure the wavefront shape. Goes through the system. You have a transmission gradient filter right there, and then propagates out to the imaging sensor plane. So we have a CMOS camera, and we use intensity measurements taken with a DX gradient filter, a DY gradient filter, and a reference filter, which is just all transmission, and use those intensity measurements to reconstruct the wavefront. So using those two orthogonal gradient filters, we can get the phase derivative of a wave function using the intensity measurements. So using the slopes calculated from the intensities, you can reconstruct the wavefront shape. It's dependent on the wavelength of laser light, the focal length of your 4F lenses, and then we use the reference intensity as like a check because our laser isn't quite the best. It's not quite Gaussian. There's some aberrations in it. So we account for any fluctuations in the intensity using the reference intensity measurement. So here's how the transition gradient filters look like. On the left is the DX filter, and on the right is the DY filter. So 0 transmission blocks all the light, 1 transmission lets all the light through. And that's how you kind of determine from intensity where your measurements are located in the focal spot. So here's some examples from using my model in MATLAB of just how the intensities look on our CMOS camera in the observation plane of one that goes through the DX transmission filter is the reference intensity, and the DY gradient filter. You can see that the intensity drops a little bit when compared to the reference intensity, but we still have more than enough intensity to get reasonable data from the CMOS camera. So just putting in a theoretical, just tilted wavefront, and using my model using a DX DY filter. That's what the 0 degree, 90 degree reconstruction means. So we started off with one wave of peak to valley within our defined pupil. So RMS is just a measure of wavefront curvature. So an RMS of 0 would be a flat wave. Peak to valley is just like the range of waves seen throughout the pupil. So started off with 1 wave peak to valley, reconstructed 0.999 waves, which is a pretty good reconstruction. And over here is the residuals when compared with the reconstruction and the known input. And we also put in a spherical wave. Same thing, 1 wave peak to valley, reconstructed a 1.01 wave peak to valley spherical wave, and then the error right there. So that's with everything modeled perfectly. Everything is in its right position, but in reality, some things can be misaligned. There's things that go off axis. So we wanted to see how much error is introduced in the system when things are misaligned. Mostly the transmission filter, making sure it's right in between those two 4F lenses. And also focal spot size on the transmission filter. You want it large enough so you can differentiate different parts of the focal spot, and you don't want it too large or you start clipping on the edges of your transmission filter. So to use this, I used a wavefront that's simulating a spherical lens of focal length 1.5 meters. There's a peak to valley of 2 waves across this defined pupil to study the z-axis misalignment of the filter. And as you can see, started off with 2 waves in the pupil, and then when it was off axis, I think by about 5 centimeters. So you start with a focal length of your 4F lenses of 1 meter. It was off axis by 5 centimeters, and it reconstructed a spherical wave with greater peak to valley and greater curvature, so it didn't quite reconstruct it as well. And the z-axis misalignment introduces a spherical aberration, also called defocus, to the wavefront reconstruction. So I used depth of field down here to see how much it was off axis. Like I said before, it was 5 centimeters. So this is at 1.05 meters away from the first lens, and this is 95 centimeters away. And it's the same error on either side of it. It's symmetric, as you can see in this graph right here. I just graphed RMS wavefront percent error with respect to the known wavefront curvature. So on either side of it, going from 2 depths of field away to on either side, introduces linear error. So then moving on to what I call like the gradient fill factor. That's the ratio of diameter of the major axis of the focal spot divided by the gradient width. So what I have here with the red lines, that's what I defined as the diameter of the focal spot. It's at the 1/e² mark of the intensity. So the ratio between this diameter right here and the full width of the transmission gradient is what I used. I used a cylindrical lens of 1.5 meters. The cylindrical lens creates like a linear focal spot like that. And what I found is that there's an optimum gradient fill factor between 75 and 85% of the total gradient width. You can see that there's error introduced from smaller focal spots where it doesn't have a large enough focal spot to differentiate the wavefront. There's optimum reconstruction right around 80%. And then you start getting rise to error from clipping and diffraction after it goes through the filter. So keeping that in mind. So I use the model to find error introduced in our system. The reconstruction is dependent on the gradient, and I went ahead and measured it. So future work with this includes studying the effect of pixel size on our transmission filter. What I showed before was a continuous filter, but what we have in the lab is a pixelated filter simulating 0 to 1 transmission gradient. So I believe the pixel size is about 10 microns on that filter. So we want to study how those pixel sizes also have an effect on the reconstruction, which will also determine the cost of developing such filters. And also finding the dynamic range of wavefront slope reconstruction of our system. We want to eventually compare the system to the commercial Shack-Hartman sensor, which coarsely samples the wavefront with a lenslet array, and it measures like local tilt using each little lenslet as a measurement point. So that's the end of my presentation. Any questions? Yes.
So, were you guys basically interested in taking the wavefront that you received from some source and then reconstructing the wavefront that came from that source?
Yeah.
Okay.
Yeah. What were you doing? So you're starting with something with a known wavefront just to make sure it was accurate, and reconstructing it. And what we eventually want to do is long term. Make a closed loop system so it can also account for things such as atmospheric turbulence and things like that. The problem with that is quickness of it. I don't know if it'll be faster than the Shack-Hartman for reconstruction, but it could also be used in like freeform optics since it will have a higher spatial resolution than the Shack-Hartman. So yeah, that's the ultimate goal.
Okay. I see. So this is just a theoretical model right now, right?
Yes.
Okay, so you guys are gonna hopefully start.
Yeah. We do have a.
The system exists.
The system does exist.
Okay.
Yeah, and we can make measurements from it, but we also just wanted to see, mostly for cost of developing a system, how well aligned things have to be before it and still have an accurate reconstruction.
Okay, cool.
Any other questions?
You said your real world filter had a certain pixel size that you're looking at. I'll go back to that. You also have a resolution in terms of how accurately the transmission is for those pixels before they get into it.
Yeah, I currently haven't studied the pixel size effect of reconstruction. I just used a continuous filter in my simulation. But yeah, that is future work, as well as the CMOS camera as well, and how well it can, its resolution affects it as well.
Any other questions? All right, let's thank the speaker again.